Our next theorem is another well-known theorem about continuous functions called an intermediate value theorem, which I'm going to state as follows. So, intermediate value theorem. We're going to suppose that we have a real valued function f that is continuous on some interval I. Then, if we have two numbers a and b that belong to I and are such that a is less than b, we have that for any y that belongs to the interval from f of a to f of b between f of a and f of b, there exists an x0 in AB such that f of x0 is equal to y. Okay. Let's try to prove this. So let's suppose that now I assume that f is continuous on I, and a and b are 2 points inside I, where a is smaller than b. So then that just means that the function f is continuous on a closed interval ab. So suppose that f is continuous on AB, and without loss of generality, we can assume that f of a is less or equal than f of b. Right, I can always assume this because vice versa, all proofs are going to look exactly the same again, but I will have to replace always f of a, interchange f of a and f of b in the proofs. Okay, so with this in mind, I'm going to choose any y between f of a and f of b. Let's try it this way. Now, if f of a actually is equal to f of b, then the proof of the statement is going to be trivial, because I can choose any x inside the interval from a to b, and the value at that x is going to be equal to y. So in that case, the proof actually is trivial. So if f of a is not equal to f of b, then we can just take an open interval from a to b and consider any y between these 2 points. All right, so let's see what we're going to get. How should we proceed? So let's try to draw a picture first, and then we will try to write a formal proof. So what we have is a function. Oops. On the interval from a to b. And I know that this function has a smaller value on the right-hand side and a larger value on the left-hand side. Now, clearly, if I try to connect these two values by a graph, then no matter which value of y I'm going to choose between f of a and f of b, then I'm always guaranteed that my graph is going to intersect the line y equal to this fixed value of y, and this will be my point x0, right? So at any level between f of a and f of b, the horizontal line is going to always intersect the graph, and so at least pictorially, the theorem must hold. How can I construct this x0? Let me actually modify this graph a little bit. Now, the graph can be pretty badly behaved. It can be a graph like this, for instance. In which case, still, at any level, the horizontal line y equal to some number between f of a and f of b is going to intersect the graph of the function. But in this general case, the intersection, there may be more than one point of the intersection. And so when I want to construct the point x0, I might want to somehow follow the rule, for instance, that I would always want to figure out either the last point of the intersection or the first point of the intersection, because that way my construction is going to be more consistent. So let's try that we want to construct the first point of the intersection just like I have drawn in here, right? So can I prove that this first point of intersection between the horizontal line and my graph exists? All right, so if it is a first point of the intersection, then to the right, or to the left actually of this point, what would I expect? I would expect that the graph of my function to the left always has to be smaller than the value of y, right? We can see it here. To the left of x0 that I'm trying to construct, I know for sure that my graph lies below y because f of a does, and there are no other points of intersection, so f of x cannot go higher than y on the interval from a to x0. So what I'm going to do then, I'm going to construct a set. So construct the set, let's call it capital S, that I'm going to define in the following way. It's going to be the set of all x between A and B, such that f of x is going to be greater or equal, actually let's just do greater, greater than y. Right, so I'm fixing this value of y, and I'm constructing this as my set of numbers S. All right, so what do I know about this set? So from a picture, right, it looks like that set will consist of the following, right? It will include all the points in this piece of a graph because there f of x is bigger than y. And all points actually up here because there all points are bigger than y as well. It doesn't matter what it is, what that set is. It includes all points x on the interval here, all points x on the interval from A to B from x0 to here, but the lowest point of this interval clearly seems to be x0. All right, so let's express this mathematically again. So then if I have this definition, number one, of course, my picture of the set S is not empty because there are a bunch of points inside the interval from A to B where f of x is bigger than y, but generically why would S not be empty? And it's easy because f of b is always bigger than y, right? Because y was chosen between f of a and f of b, so b then must belong to the set S. So S is not empty. So S is not equal to the empty set because B is an S, right? Again, that is true because f of B is bigger than y. All right? Then number two, because S is not empty, it's a non-empty set of real numbers, which is bounded from below by A and from above by B. So S is a bounded set of real numbers, and therefore infimum of S, let's say equal to x0, it exists. And moreover, because the set S is completely contained inside the closed interval from A to B, x0 is also an element of AP. Okay? Number three. What is the value of f at x0? Let's discuss that. Well, so from a picture, clearly value of f at x0 is equal to y, and that's what I want to prove, right? Because I'm trying to show existence of this set of the point x0 where the value of f is equal to y. So I already identified a candidate x0. Now I need to prove that the value of f at x0 is y. Okay, so let's now do this. For every n in n, the number x0. Okay, let me see. For every n in n, one moment. So for every n in n, x0 plus 1 over n is not the infimum in fact, it's not just, it's not the infimum of S, but it's not a lower bound on S, and this is because x0 is the greatest lower bound on S. Right, and from that, I can conclude that there exists an xn in AB such that, or actually not in AB, but even smaller in S, such that f of xn is going to be, because xn is in S, is going to be greater or equal than y, right? Because if xn is an S, then it's the value of the function at xn must be greater than y. And xn belongs to the interval from x0 to x0 plus 1 over n, right? That is again because x0 is the infimum, and so if we increase the infimum of S, so if we increase the infimum by some small amount, then between the infimum and this increased number, we should be able to find an element of a set. All right, so in that case, I got a sequence xn, right, where xn belongs to the interval from x0 to x0 plus 1 over n. So if I use a squeeze theorem, and I take a limit of all three sides in the inequality, limit n goes to infinity of x0. I take a limit n goes to infinity of xn, and I take a limit n goes to infinity x0 plus 1 over n, right? Then the comparison principle tells me this, and because the limit of a constant x0 is x0, and the limit of x0 plus 1 over n is also x0, again by the squeeze theorem, we have that the limit n goes to infinity of xn is equal to x0, right? So that is clear. Now, because xn's belong to S, so also xn belongs to S for any n, right? And so therefore xn belongs to AB for any n, right? Just because S is a subset of AB. And then because F is continuous on AB, we have that F is continuous at x0 in particular, right? And therefore, so F is continuous at every xn, and F is continuous at x0 because x0 belongs to the interval from A to B as well. Now, which one of these I can use? Well, I can use a continuity at x0. If xn converges to x0, then by definition of continuity at x0, continuity at xn seems to be irrelevant. We have that the limit n goes to infinity of f of xn must be equal to f of x0, right? But we said that f of xn is greater or equal than y for all xn. And so therefore, so f of xn greater or equal to y for any n, so that means that the limit on the left is going to be greater or equal than y, and so therefore f of x0 must be greater or equal than y. Right, so once again, let me try to repeat this argument. X0 is a lower bound on the set S, so therefore x0 plus 1 over n is not a lower bound, because x0 is the greatest lower bound on S. And so then for any n, there exists xn in capital S, such that xn belongs to the interval from x0 to x0 plus 1 over n, right? Because x0 plus 1 over n is not the infimum. And because xn belongs to S, then we have that f of xn is greater or equal than y, because that was the definition of the set S. All right, so then we observe that because xn is sandwiched between x0 and x0 plus 1 over n, by using a squeeze theorem, we get that the limit of xn must be x0. And then f is between a and b, function is continuous on AB at every point of AB, so therefore it must be continuous at x0. And so then I can use a sequential definition of continuity. And it tells me that as long as I have a sequence which goes to x0, then f of that sequence should go to f of x0. But also all f of xn are greater or equal than y. So if I take a limit of numbers greater or equal than y, I'm going to end up with something which is still greater or equal than y, and so that is the conclusion. So now I also want to show that f of x0 must be less or equal than y, because if it is, then I'm done. The number can only be greater or equal than some other number and less or equal to that number if those two numbers are exactly the same. So let's do number 4. And here let's introduce another sequence. So let Tn be equal to the maximum of a and x0 minus 1 over n. And this is for any n, which is a natural number. Okay, so then Tn belongs to the interval from a to b, not x but x0. Right, because we're looking at numbers here which are lower than x0 but not higher than a. In fact, yeah, so that's what we got. So then all Tn's belong to the interval from a to b, again, for any n greater or equal than 1, or just repeating what I wrote in the previous line, for any n in capital N. And Tn does not belong to S because Tn is smaller than x0, right? And x0 is the smallest number that belongs to Tn. So this is infimum of S. Okay, but then because Tn does not belong to S, how did we define S? S consisted of all numbers which are greater or equal than, at which, of all x's at which the value of the function is greater or equal than y. So that means that f at Tn, because Tn is not in S, f of Tn must be smaller than y, right? Again, this is true for any n in n. All right. And so then, what do we know? We know, just like in the previous example, right? Tn is a maximum of a and x0 minus 1 over n. So as n goes to infinity, then Tn should get closer and closer to x0, right? And so let's write this down. Then the limit n goes to infinity of Tn must be equal to x0. And again, because f is continuous, at the point x0, then by definition of continuity, we conclude that the limit n goes to infinity of f of Tn must be equal to f of x0. Right? If Tn goes to x0, then f of Tn should go to f of x0 because f is continuous at x0. All right, but on the other hand, we have that f of Tn is less than y for any n in n, and so even if I could take a limit of both sides in this inequality, so then by comparison. Limit n goes to infinity of f of tn becomes less or equal than the limit n goes to infinity of y, which of course is just y in this case. Why is the limit less or equal, right? Because if I have a sequence of numbers which are below 1, strictly below 1, that sequence still can converge to 1. All right, and so what we got is so limit of f of tn is again f of x0. So we have f of x0 less or equal than y from here. And from phi, we have that f of x0 is greater or equal than y. So f of x0 must be equal to y. And the theorem has been proved. Next time we will look at consequences of the intermediate value theorem and extreme value theorem.